This tutorial is about aluminium bracket using plane stress. In this example, in this bracket, all the dimension is given as follows, and the material properties is 69 gigapascal, and the Poisson ratio is 0.3. Three holes are fully constrained by screw, and the pressure applied to the side surface is 10 Newton per millimeter square. First, we are going to create the parts. So double click on the parts and we name it as bracket. And we are using 2D planar and show features and approximate size is 4. This is the sketch of the bracket. We are going to model half of it because the model is symmetric about y-axis. After that, we click Done. The material property we have specified in this is 69 gigapascal and the Poisson ratio is 0.3. And after that, we click OK. The next step is to create the section assignment. Double click on the section assignment. Next, select the whole region and followed by Done. After we click Done and the edit section window will appear, and we click the red box and correct section assign bracket will be appear, and click continue. The next step, edit section window will appear again. So we are going to take the plane stress or strength thickness. In this case, we using plane stress and we specify the thickness is 0.0015. After that, click OK. So after we click OK, so the edit section assignment window will appear again. So in this case, so the type is solid homogeneous, material is material 1, and we click OK. If everything is done correctly, and the turquoise color of your bracket will be appear on your screen. The next step is to create the instances. Double click the instances and the create instance window will appear. So in this case, we are going to use independent rather than dependent. This is because the pressure we apply on the surface is split into two different sections. So we are going to choose the lower section and we apply the force. Therefore, we need to use independent rather than dependent, followed by OK. So the next step is to create the step. Double click on the step and the create step window will appear. So in this case, so we are going to choose linear perturbation and static linear perturbation and click continue. After we click continue, an edit step window will appear and we click OK. So the next step is to create our boundary condition. The first boundary condition is symmetry. Okay, so we select mechanical symmetry under selected step, click continue. After that, we are going to select the vertical as shown at the arrow. This is because our model is symmetric about vertical axis, and click done. After we click done and the edit boundary condition window will appear. So in this case, so we are going to select X symmetry because our model do not move horizontally, and followed by OK. After we click OK, so the next boundary condition we apply is the hole. So in this case, so we are going to choose symmetry again and click continue. After we click continue, we select the hole and followed by done. After we click done, so in this case, so edit boundary condition window will appear and we are going to select encastre because the XYZ direction of the hole is not going to move because it is fully constrained by a screw, and followed by OK. The next step is to create partition before we apply loads. So click on the Tools, Partition, and the Create Partition window will appear. Select Edge and select Midpoint or Datum Point from the screen. Okay, so in this particular screen here, so we are going to select a point on the edge. Then we follow by click on the vertical line again, and next is to click on the Create Partition. After we create the click partition, and you will realize the vertical line will be split into two different sections, whereas the red yellow dot will be a midpoint of the vertical line. The next step is to create our lots. Double click on the lots and the create lots window will appear. In this case, so we are going to select pressure and click continue. After we click continue, so we are going to select the lower vertical line and click done. Okay, as we remember, the pressure we apply is 10 Newton per millimeter square. However, when we draw our model, we're using SI unit meters. Therefore, we are going to change Newton per millimeter square to Newton per meter square. In this case, so 10 Newton per millimeter square will be equivalent to 10 mega Newton per meter square, or I can say 10 megapascal. So in this case, so we are going to enter the magnitude as 10 power of 6. And we can click OK. So the next step is to create our mesh. Double click on the mesh under instances. And next, we are going to select Seed Edge. So the first step we are going to select is the curve. So we are not going to use the global mesh. We are using the assign the mesh size at each particular line. So in this case, so we are going to select the curve or the circle as one mesh size, and the vertical line or the horizontal line will be another mesh size. So in this case, so we are going to select the curve or the circle. Then after that, we click done. The next step is after we click done, and the local C window will appear. So in this case, so we are going for the curve, the element size is 0.004, and we click OK. After that, continue to select the remaining line for the horizontal and vertical line. So in this case, so we are going to specify it as 0.006, which is a slightly larger mesh size compared to the curve. If we did correctly, so this will be my seed, and click done. After we click done, so we are going to select the element type. So select the whole bracket and followed by done. And the element type window will appear. So in this case, so we are going to choose plane stress and untick the reduce integration, followed by OK. Then finally click done. So the next or final step is to mesh our model by click the mesh at the menu bar, followed by instant, then followed by yes. So our model will be meshed properly. So the final step is to create our jobs and submit our model to perform the analysis. Once the job is completed, we may view the result. So in this case, so our first result we are going to see is the wall mixer stress. So the curve mesh size is 0.04 and the line mesh size is 0.006. So I'm going to export my solution in the output file. So in this case, so the maximum stress is 309.846 power of 6, and the maximum element number is 1741. Okay, we are going to repeat different mesh size. Before changing the mesh size, so I suggest to create a new job using different name. This is because when we change our mesh size, we do not want to change the previous solution, which you can view it later stage. So in this case, so I'm going to name it as different name, okay, as you like, maybe solution 2, and click continue. After we click continue, so we may change our new mesh size for, let's say, in this particular example, so I'm going to choose for the curve or circle, I'm going to use 0.003, and for the line, so which is referred to horizontal or vertical, is 0.006. After we have changed our element size, so we are going to mesh it again. After that, we are going to submit our job to perform the analysis. Once the analysis is done, so this will be my second solution. So in this case, so you will realize that the maximum stress is 314 and the maximum element number is 2176. Keep repeating. So the next one is 0.002 for the curve and 0.004 for the line, and the solution will be here. So the maximum stress is slightly larger compared to the previous, as this will be 317 megapascal, and the maximum number of element is 4709. So the next one will be even smaller elements as mesh size, and this will be contribute to the maximum stress of 325 megapascal, and the number of element is 5826. The next one will be 0.001 for the curve, and the line is 0.003, and the maximum number for the stress will be 330 megapascal, and the element number will be 120554. Why we need to do so using different methods? This is because we need to find the convergence test. In this case, so I realized that I have done at least 5 different meshes, but I realized that the solution is not converged yet. So therefore, I'm going to choose another smaller mesh size. So in this case, so for the curve and is 1 millimeters, and for the line is 2 millimeter mesh size. So in this case, will be the maximum stress is 330 megapascal, and the maximum element number around 20,000 elements. So in this case, so I'm going to summarize in the table, and I found out that the last two rows, the error between them is around 0.004%. This will be quite small. Therefore, I'm going to plot it in the graph. In this graph, so there are 6 different points, and this is obtained from the solution which you have done earlier. After that, we are going to plot a polynomial curve to see where the line will be enough convergence or not. Okay, so in this case, so I found that the element number around 12,000 is going to converge around 330 megapascal. So in this case, so we can say that if we use that particular element size is sufficient to run the simulation. So the next I'm going to show you is the displacement of the converged solution. Okay, so in this case, so we are going to select result and select the field output, followed by U displacement at nodes, and click OK. So in this case, so you will see on your screen, this will be the displacement at the total displacement. So the maximum displacement corresponding to the converged solution is 2.439 times 10 to the minus 3. So in this case, what is in meter? Because when we draw our model, we use SI unit, so therefore is meters, or I can say that is 2.439 millimeters. Okay, so this will be the final solution. Thank you.